Continuing the design of my motor controller, in this video I'm going to be adding button inputs. I've modified this diagram a little bit and I added hardware watchdog because I think that is going to be very useful. It's going to be a way to guard against runaway programs on the STM32. And also if STM32 for any reason enters into a fault condition and just logs up, then hardware watchdog will reset the drive and hopefully avoid any problems where the motors would be driven and the STM32 would be locked up. So I really have to consider hardware watchdog. I'm not sure if I'm going to be doing a discrete circuit with a capacitor and a Schmitt trigger and the resistor where the chip has to supply pulses on a GPIO pin, or if I'm going to use an IC that implements this functionality. So I'm going to look at that in one of the later videos. In this video I'm going to be handling this part. This is going to be a number of input connectors with plug terminals where the user can connect switches. And we all have seen typical debounce circuitry for switches where you have a capacitor and a resistor, and the capacitor and resistor act as a low-pass filter and filters the noise that occurs when the switch precisely sort of when the contacts touch. However, that solution is not very good because it doesn't handle the ESD protection. So if we were to use that solution, we would have to add the ESD protection, which kind of adds up to the whole circuitry. And I'm going to show you a circuit that does the key debouncing within the integrated circuit. So this is what the typical signal looks like when the key is pressed. So there will be a lot of noise, and if this is used to trigger an interrupt, then we really have to do some kind of filtering here, because we're going to trigger the interrupt multiple times when the key is pressed. So this is not good. This is something we want to avoid. The simplest way to avoid that is to put a resistor and a capacitor. And so when the key is pressed, the capacitor discharges through this resistor, and when the key is released, it charges again through this resistor. This pretty much removes the noise that comes in the beginning when the key is pressed. However, we also have to use over voltage protection, and we also need to possibly add a Zener to make sure that we don't overdrive the power lines, especially when the circuit is powered off, and things like that. So it kind of, and then we have to have a Schmitt trigger as well. It's kind of too much, because we have to have a Schmitt trigger because we are running at 5 volts on the inputs, and technically this could be an input that is not just a key but something else that pulls the line high or leaves some higher voltages on this connector when the power is powered off, things like that. All of these things are adding up to the number of discrete components that I would have to use. So Maxim Integrated has come up with this solution called Max 6818, which implements this circuitry and does key debouncing, and also has pretty good protection, and it looks like this. So there is a little timeout for when the key is pressed, and then you can see when the noise occurs there is a small timeout, and then the signal goes low there. And the same thing happens for when the switch is pressed. So this is a nice chip to avoid any discrete components on these inputs. So I'm going to use this chip, and I'm going to wire it up to, let's see, here's the datasheet for this chip. And I'm going to wire it up to the processor inputs, and the inputs of this chip are going to be wired to connectors that go to switches. The VCC of this chip is up to 6 volts, And I think that output high level is, let's see, I think the output high level is, let's see, input threshold, minimum 2.42 volts, and output voltage is, let's see, so low is at most 0.4 volts and the VCC minus 1 volt at least. We're going to run this chip at 3.3 volts, and input threshold for 3.3 volts is going to be slightly over 2 volts, which is good, which is okay. So the inputs are pulled up so that when the button is not pressed, they are active high, or they are high. And when the button is pressed, they go low, and the output goes low after a little delay there. So I'm gonna add this chip. I already have it in my library. Let's see, max 6818, and the inputs here. Let's see. Did I add a symbol here? Switch. Yeah. So I'm going to remove this pin there and just rename this to GND. This would be an input, or actually this would be, yeah, this could be like a power input, and this would be an output from the symbol, that is. So any other components that are connected to this symbol will see this as an output. And this output would be switch. Yep. And I'll move this one a little bit there, and can move this one to the middle. And I also need to update the, let's see, the footprint. Terminal block. 4 Yukon 1 times 3, 1 times 2, 3.5 vertical, horizontal, I think it's that one. I'll double check this. I'll double check the measurements a bit later when I go to PCB layout. So let's add this switch input. And the reason I have 2 pins per switch is because I don't want to have a bunch of inputs and just one ground. So I want it to be easy to add new, to add switches to connect them. What the user will do then is use the screw terminals on the plug to connect the wires that go to the switch, and then plug the plug connector into this header, which will be on the PCB. So I'm going to copy this, and let's move this like that, and then copy. So you may think that 8 switches is too much, but in reality it actually gets used up quite quickly, because keep in mind that these switches can also be used for the motor switches, where you have limit switches. So if you have 2 motors, then let's say you use 2 limit or 4 limit switches. and you used up all of these connections. If you need to connect the limit switches. Now, if you have a linear actuator, then limit switches will just disconnect the motor power to the linear actuator, to the motor inside it. But there could be other switches. There could be like, for example, switches that are used for detecting the 0 point, so that would be, let's say you have two motors, so you use up two there. Then you may have two switches that determine direction of each motor, and let's say that these two switches would be a three-position switch, so it would connect either this one or none of them. So then you used up two more. So eight inputs is kind of the minimum, I would say. It's very easy to just realize that even having 8 inputs is not enough. So I'm going to connect the grounds, and I will then connect the switch inputs to this chip. Copy that one, and going through the inputs here. So for once, I won't have to care about key debouncing. Not in code and not in hardware. Besides putting this chip on the PCB, of course. Yeah, so move this one up here, because that one is the enable input. And then we have the 8 switch here. Great. VCC will go to, let's see, connect this to 5 volts, or 3.3 volts, sorry. And then capacitor goes to ground. Okay, VDD3 will go there, and then we have enable. So a switch enable, let's call it like that. Switch 1, switch 2, switch 3, switch 4. So there's going to be a small delay, and this will be RQ. RQ, and switch 2. Switch 3, edit switch 4, edit switch 5, switch 6. I think there's like 60 milliseconds or something almost seems too much. So this would be 7, and this would be 8. Switch 8. I'm going to check the datasheet again. Debounce delay, debounce duration, typically 40 milliseconds. So if this would be used for a switch, like a limit switch, then in 40 milliseconds, yeah, 40 milliseconds is a lot. It would be nice if this interrupt would fire when the pin starts changing or something. Although it's kind of useful to have both. So that's input, and then output is delayed by 40 milliseconds. And the change pin goes low when the output is changed. So there's really, it's kind of, there is no reason to have this change pin when it actually only changes when the output here changes. Like we can assign interrupts to these pins directly. It's not necessary to have an extra pin there. Okay. It would have been far more useful to signal when the input signal just starts to jitter. So to change the CH pin here. But okay, we'll have to live with this. We'll have to have some other way of connecting limit switches that to which the motor drive has to respond quickly. Let's say we're moving, so if we're moving 1 meter per second, we're going to have 40 millimeters delay, which is a lot. It's not instantaneous response. But for things like buttons and user switches, this is perfect. Okay, so this one seems to be done. I can't see anything else I need to add here right now. I may come up with something I need to add later. I think there is input resistors as well in this chip. Let's just double check the diagram. Yes, so there is a pull-up resistor, there is ESD protection, there is input resistor, there is over voltage protection. Yeah, everything is inside this package. So nothing else to add here. This is going to be connecting the outline here, make it into a pretty little drawing like this, and done for now. So I can go back to this diagram here and set the switch input to green using the third value there. So now about the digital I/O. So basically, digital I/O, the SPI I2C, brake control, and any let's see, and any GPIO based interface. For that, I'm going to use a buffer, which is called TSC. I think it's called TSC something, from Texas Instruments. It is a bidirectional buffer that allows interfacing 5-volt circuitry to 3.3-volt circuitry. TXS0108. So this chip supports on one side 3.3 volts, on the other side 5 volts. You have two different power supplies, and you have output enable, and then these pins are bidirectional, which is very good, so that these can carry any signal, including I2C or serial interface or SPI, and it will translate them between 3.3 and 5 volts. So I'm going to add this chip, but I'm not going to assign any connections. TSC, no, what was it called? T something, TXS. Let's see. Yeah, you can call this expansion IO, and I'll just add the capacitor here on each of the voltage rails. Capacitor will go to ground. Copy this ground reference, and then we have 8 pins that I can use for something that will be left over on the chip. So when I've connected all the pins, all the necessary pins, then I'm going to connect these GPIOs to any pins that are left. And this will probably be a connector that connects to a flat cable or something. VDD 3v3, let's see. And VDD 5 volts. Actually 3v3, yeah, we can just copy this and rename the other one. So 3v3 will be here, and this will be 5 volts. So this will provide a means of interfacing with 5-volt inputs. Great. I'll leave this for now, and I'll continue. Let's see, what do we have left here? We can make digital I/O, brake control, and SPI, and let's see, and this one, we can make them gray, meaning that I'll handle them later. and actually even the PWM in is going to be connected through a buffer like that. So I can grey that out as well. Next we have temperature sensing, EtherCAT, USB, LCD, and watchdog. Out of all these things, and also the power supplies, the main power supplies. So there will be 5 volts, and there will actually be 48 to 12 volts, I think. And the 12 volts will come out on the connector, and then there will be 12 to 5 and 5 to 3.3. But out of all these things, I think EtherCAT interface is going to be the most complex one. Great. I'm going to stop this video now. Thanks for watching.